So let's consider an example of the impact of winds blowing over the surface of the ocean on ocean circulation. So if we've got, for example, the westerlies blowing from west to east along the mid-latitudes, and beneath that, near the just north of the equator, we've got the trade winds blowing along from east to west. What that creates is differences in ocean transport. So remember that in the northern hemisphere, the average deflection of the surface waters of the upper ocean due to the wind is 90 degrees to the right. So what that means is that the westerlies blowing over the surface of the ocean in this direction are going to impart a circulation or a force on that water that's going to transport any water that's up here down to the south. Okay. Conversely, in the trade winds, we've got trade winds blowing in this direction, and so that means 90 degrees to the right means that water is going to have a tendency to be transported to the north. And so this causes a buildup or convergence of ocean currents and essentially ocean water. So that water, that wind pushes against the surface of the ocean, and it's pushing those waters together, creating a convergence. So if we were to plot as a function, if we were to plot sea surface height as a function of latitude here on this same plot, what we would see is we have this buildup of high sea surface heights in the center of this convergence zone here. And so this essentially creates a doming of surface waters and doming of the surface of the ocean in this convergence zone, where we get essentially high pressure buildup of seawater. What this does is this is a typical feature found throughout the subtropical gyres of the oceans. So subtropical gyres. So we've got, if we've got a continent here and we've got another continent here, ocean in the middle, we've got the westerlies blowing this way, the trade winds blowing that way. What we get is this high pressure system, and balancing that sea surface height is going to be this pressure gradient effect. So that water is going to want to move away from this, because it's domed up, it's going to have a tendency to want to move back and re-equilibrate and flatten out that sea surface. And as it does so, that water moves around it's also deflected in the right direction in the northern hemisphere, and creates this this clockwise circulation in the northern hemisphere subtropical gyres, and this drives a weak downwelling as waters converge in this subtropical gyre, and this circulation around the this high pressure ridge where we get this this clockwise circulation, and so this is the driving structure of what happens in the subtropics. Conversely, if we look at what's happening at the equator, we've got the trades moving that way to the north of the equator, and the trades moving to the west to the south of the equator. And because the sign of the Coriolis effect switches directions here, we get a we get two different surface water transport directions. So in the southern hemisphere, that surface water is transported to the south, and in the northern hemisphere, it's transported to the north. So instead of convergence in the case of the subtropical gyres, we actually get divergence along the equator. And this drives that separation of waters is pulled apart, that divergence is replaced from waters that are even deeper below the surface in a process termed equatorial upwelling. Equatorial upwelling. So it's these major features across the ocean driven by winds that are creating major circulation features that in turn impart patterns on the distributions of chemicals and biological properties, biogeochemical properties throughout the ocean waters. So this is has a big structuring effect on ocean chemistry. So winds blowing over the surface of the ocean near the coast also have a specific effect on currents, and so they can create coastal upwelling or coastal downwelling. So if we look at the side view of here's the coast, and here's the oceans, here some mountains, and if we have winds like blowing out of the page. So this is the tip of an arrow, and it's pointing. It's blowing out of the page. What happens is that's going to in the northern hemisphere, that's going to drive a net offshore transport 90 degrees to the right of the wind. Of surface ocean waters. And so this water is moving away from the coast at the surface, and that water has to be replaced somewhere. And so in addition, the sea surface height slightly decreases in the alongshore region as these winds are strong. And when those waters move offshore, it draws new waters up from deeper and offshore and brings those up to the surface. And so the effect of this is that we've got upwelling of deep, cold, and often nutrient-rich waters that are transported up right next to along the coast. And so examples of this are the California and Oregon coasts, for example, where especially during the spring, summer, we get some strong winds coming out of the north, blowing south along the coast, and that are driving waters offshore, pulling up those cold, deep, nutrient-rich waters. And that's part of what's driving a lot of the enhanced productivity of fisheries and the ecosystems, marine ecosystems along the U.S. West Coast. Another example is the Benguela upwelling system. Conversely, as we look at, if we look at the Gulf of Alaska coast, this wind is actually blowing in the opposite direction. It's blowing into this page in this example, and so that creates an opposite pattern of waters being drawn from the surface offshore, inshore, and displacing waters and creating a generalized downwelling effect. And so that's characteristic of the Gulf of Alaska throughout much of the year. And so it's these different winds and the orientation of the prevailing winds relative to the coasts that can impart currents on the surface oceans and therefore drive transport of deep waters up to the surface or down from the surface into the deep. And this impacts nutrient distributions and biological productivity in these particular regions.